In the previous video, we introduced Big O notation and began learning about algorithms. In this video, we're going to take a look at how we can improve our performance by caching computations. We'll then look at the classic Memoize function and test its performance. The most common implementation of memoization was introduced in WWDC 2014, session 404 on Advanced Swift. In this video, we're going to break down the Memoize function as it was introduced by Apple and measure it as we go. Memoizing is a way of improving the performance of functions that perform the same computations over and over again. We do this by introducing a caching mechanism that stores the results of the expensive computation. With the results of our computation stored, we can then simply return the cached value of the computation based on the input rather than reperforming the operation. We'll start with a simple non-generic Memoize function. Then we'll introduce and deconstruct a generic version. Create a new Xcode project with unit tests. Once done, add a new Swift file and name it Memo. We'll add a class with the same name and define a simple function that generates a sequence of Fibonacci numbers. For this first test, we're going to modify this function to print out our values so we can visualize how complex this computation really is. Of course, printing also takes CPU power, so we'll remove it for our later tests. Next, let's wrap our call to fib so we can call this function from our unit tests. We'll start by creating a new function that takes an int and passes it along to a call to our fibs function. I'll name this function fibwrap and simply call my fib function, passing along my parameter. This is all we need to establish a baseline test. In your test suite, add a placeholder for an instance of your memo class, and then initialize it in your setup function. You can set your instance to nil in your teardown function if you choose. Next, we'll add a call to our fibs function and pass in a value of 28 to see some activity in our console window, and we'll run the test. Obviously, this test is flawed due to our print statement requiring CPU power, but this does serve to illustrate how much work is being done to generate 28 levels of Fibonacci numbers. Notice in this continuous stream of numbers how many of them are repeated. This is a strong indication that we're making the same computation over and over again. More on this in a moment. Let's remove that print statement and then rerun our tests. It finishes quite a bit faster since we aren't printing each value as it operates. Let's up the number to 45 for a more substantial set of operations, and we'll run the test. This time, our operation takes well over 10 seconds to complete. This drastic time increase is because the order of complexity of this operation is exponential, or O times 2 to the nth power. We saw in our first test how many repeated computations were occurring. We can introduce a caching mechanism that stores references to these computations to avoid the extra work. Above our fib function, we'll create a new dictionary that will act as our cache. The key will be an int and the value a double. Then, at the top of our fib function, we'll check our fib memo dictionary for a key that matches our input's value. If the key exists, we'll simply return our stored computation result and forego further computations. If the value does not exist in our dictionary, we'll proceed with our computation. Then, below our computation, we'll take the result and store it in our dictionary, using our function's input for the key and the computed output for the value. Then we'll return our result. If we run our test now, we should see a much different result due to our newly installed caching mechanism. And we do. We see that our computation was completed in less than 1/1000th of a second, which is a staggering difference from the non-caching version. And this operation can be done using generics, making our Memoize function more useful in general. For brevity, we'll paste in a generic Memoize function and break it down line by line. So this is Memoize, as it was presented by Apple in session 404. We'll start our deconstruction at the method signature. First, we see that our Memoize function accepts a dictionary whose key conforms to the hashable protocol and is represented by the alias t, while the dictionary's value can be of any type and is represented by the alias u. Next, we'll look at our single parameter, which takes a function. The input function itself takes two parameters. The first parameter is yet another function that takes a type t and returns a type u, while the second parameter is of type t. Finally, our input function returns a type of u. Our Memoize function itself also returns yet another function that takes a type t as its input and returns a type u as its return type. Next, we see our variable named memo, which is a dictionary that matches our input dictionary. This represents our cache. Then, we have a result placeholder, which will contain a closure, which, in the next line, gets its value. The closure we're assigning to result first checks our cache for the existence of a stored computation. If one exists, we simply return the stored computed output. If one does not exist, we'll perform our computation by calling our passed-in closure and providing it our result along with our key to compute a value. Then we store our computed output in our dictionary and return our value from our closure. Finally, we return our result. Now let's put this Memoize function to work. We'll start with a simple wrapper function named memowrap, which takes an int and returns a double. Then we'll define a new constant named Fibonacci, which will also get a type of takes an int and returns a double. We'll set it equal to our generic Memoize function, and we'll paste our Fibonacci computation into its closure. Now let's rewire the test and use our Memoize function. That should do the trick. Upon running our test, you see that we get similar times to our previous cached version. Before we move on to the next video, I wanted to once again point you to Colin Eberhardt's Game of Life tutorial. As I mentioned at the beginning of this course, our version of Game of Life was based on Colin's version over at scottlogic.com. If you want to learn how to utilize memoization to drastically improve your Game of Life, follow this link over to Scott Logic and see Colin Eberhardt's excellent demonstration. You can find a direct link on this video's resource page. In this section, we learned how to measure and inspect our application's performance with Time Profiler and XCTest. We saw how whole module optimization gives us a free performance boost and how we can improve those performances by reducing dynamic dispatch and reference counting. We also learned about how the generic specialization optimizer improves the performance of our generics. Finally, we introduced Big O notation and algorithms like Memoize. In the next section, we'll look at some common design patterns implemented in Swift.